When you picture a black hole, what comes to mind is a cosmic vacuum cleaner, sucking up anything that ventures too close. But have you ever wondered what happens when the universe's most monstrous black holes go on an all-you-can-eat buffet? It's not just a chaotic feast. It's the birth of a phenomenon so bright it outshines entire galaxies. Today, we're joining a quest to the heart of quasars and uncovering the mind-bending physics behind their incredible light. Today, we are taking you on an exhilarating journey beyond the confines of a black hole's event horizon, where space and time warp into an enigmatic realm of intense gravity and unfathomable energy. Our destination is the immediate neighborhood of a blazing quasar, a place of extremes where matter is heated to millions of degrees, and where light itself dances in a cosmic ballet of swirling magnetic fields. The energy generated by these beacons is truly staggering, reaching billions of times the luminosity of our sun. To put this into perspective, if our sun were as bright as a quasar, it would outshine 24 million Milky Way galaxies, each containing trillions of stars. We'll delve into the remarkable process by which quasars convert gravitational potential energy into light, explore the powerful jets that propel material from the poles of the accretion disk, and reveal the fascinating ways in which quasars influence the evolution of their host galaxies. This is more than just a journey to the edge of a black hole. It's a voyage into the heart of some of the most luminous and influential objects in the universe. So fasten your seatbelts and prepare for a journey beyond the known, where the laws of physics are rewritten and the boundaries of the cosmos are illuminated by the blazing power of accretion disks. We're standing at the precipice of a black hole. But this isn't just any black hole. It's a supermassive black hole, a behemoth residing at the core of most major galaxies, including our own Milky Way. Its gravitational pull is so strong that not even light can escape its clutches once it crosses the event horizon, the point of no return. But here, just outside the horizon, we find ourselves in a region of immense energy and activity. Here is where the magic happens, where the raw power of the black hole is transformed into some of the brightest and most energetic phenomena in the universe, quasars. As we peer into the heart of a quasar, what we see is primarily an accretion disk, a swirling vortex of glowing gas and dust. This disk is the key to understanding the immense power of quasars. It forms as material, mostly hydrogen and helium gas, drawn in by the black hole's gravitational pull. As the gas approaches the event horizon, it accelerates, heating up to millions of degrees. This intense heat causes the gas to emit light across the electromagnetic spectrum, from radio waves to X-rays. But it's not just a simple accretion process. The material doesn't fall directly into the black hole. Instead, it forms a thick disk around the equator of the black hole. This is due to the conservation of angular momentum. As the material spirals inward, it collides with gas and dust, creating a shock wave that heats the material even further. This creates a bright, luminous ring around the black hole. The inner part of the disk is very hot and emits X-rays, while the outer parts are cooler and emit visible light and radio waves. Quasars are among the brightest objects in the universe, powered by the gravitational energy released as material is pulled into the central black hole. They can be found at the centers of both large and small galaxies, but they are most common in the early universe. While most black holes grow steadily over billions of years, the growth of supermassive black holes has been both rapid and prolonged. Some grew extremely fast during the first few billion years after the Big Bang, consuming vast amounts of gas and dust and shining brightly as quasars. Others grew more slowly, but have been active for most of cosmic history. The growth rate of a black hole determines whether its accretion disk shines as a quasar. If it accretes material rapidly, it will shine brightly. If it accretes material slowly, it will emit faint light, becoming a low-luminosity quasar or a radio galaxy. One fascinating aspect of accretion disks is that they are not only found around stellar black holes, but also around neutron stars and white dwarfs. However, the accretion disks around these compact objects are much smaller and fainter than those around supermassive black holes. For example, when a stellar mass black hole with about 10 times the mass of our Sun accretes material, its luminosity can reach about 100,000 times that of our Sun. On the other hand, when a neutron star with about 1.4 times the mass of our Sun accretes material, its luminosity can reach about 100 times that of our Sun. Similarly, when a white dwarf with about the mass of our Sun accretes material, its luminosity can reach about 10 times that of our Sun. These differences in luminosity arise because the mass of the central compact object determines the strength of its gravitational pull, which in turn affects the rate at which it can consume and release the energy of infalling material. Around quasars, the accretion disk is only one piece of the puzzle. Jets of high-speed material are ejected from the poles of the disk, extending thousands of light-years into space. These jets are powered by the rotational energy of the disk and play a crucial role in the evolution of the host galaxy. But these magnificent displays of energy are not just aesthetic spectacles. They are powerful engines that drive galactic evolution, influencing star formation and regulating the growth of their host galaxies. This is a testament to the profound impact these enigmatic objects have on their surroundings. Now let's talk about ignition. What's the secret behind the blazing light of an accretion disk? It all boils down to energy conversion. As the material spirals inward towards the black hole, it loses gravitational potential energy. This energy is then converted into heat and light, causing the disk to glow with an intense brilliance. The temperature of the disk varies with location. The inner regions, where the material is closest to the black hole and gravitational potential energy is at its maximum, are the hottest, reaching millions of degrees. These regions emit high-energy photons, including X-rays. As we move outward, the temperature decreases and the emitted light shifts to lower energies, encompassing the visible light spectrum and beyond. The outer parts of the disk are cooler and emit radio waves. Thus, an accretion disk is not just a single source of light, but a broad spectrum emitter, bathing the surrounding space in a radiant glow that spans the electromagnetic spectrum. The sheer luminosity of quasars is truly mind-boggling. These celestial giants can outshine entire galaxies from a region as small as a few light days across. Our Sun, for comparison, takes about 8 minutes for its light to reach Earth, covering a distance of about 150 million kilometers. In contrast, a quasar's light originates from a region less than 1 light day across, making them incredibly compact sources of immense energy. At their core, supermassive black holes serve as the gravitational anchor, driving the formation of the accretion disk and powering the quasar's blazing light. These black holes, millions or even billions of times the mass of our Sun, exert a gravitational force that draws in vast amounts of gas and dust. As this material spirals inward, it forms a glowing disk around the black hole, emitting light across the electromagnetic spectrum. The energy released by the conversion of gravitational potential energy into heat and light is what makes quasars some of the brightest objects in the universe. Looking beyond the immediate vicinity of the black hole, we find powerful jets of material being ejected from the poles of the accretion disk. These jets extend thousands of light years into space and are powered by the rotational energy of the disk. Quasars are not just cosmic powerhouses, but also key players in the evolution of their host galaxies. Their radiation and powerful jets significantly affect their host galaxies and the surrounding intergalactic medium. This effect is known as cosmic feedback. Quasars can either trigger or suppress star formation in their host galaxies, depending on the balance between the energy they inject and the material they consume. This feedback plays a crucial role in regulating the growth and evolution of galaxies throughout cosmic history. As we continue to explore these blazing beacons, we hope to gain a deeper understanding of the complex interplay between supermassive black holes, their host galaxies, and the evolution of the universe itself. From the smallest details of accretion disk physics to the largest scales of galaxy evolution, quasars offer a rich and dynamic area of study. And as our observational capabilities improve, we can expect to unlock even more secrets of these extraordinary objects. In the quest to unravel the mysteries of quasars, we turn to the James Webb Space Telescope, a cutting-edge observatory poised to revolutionize our understanding of these distant beacons. With its advanced infrared capabilities, the Webb will allow astronomers to peer deeper into space and time, observing quasars as they existed just a few billion years after the Big Bang. By studying the light from these early quasars, scientists hope to gain insights into the formation and evolution of the universe's first galaxies. Additionally, the Event Horizon Telescope, a global collaboration of telescopes, aims to capture the first-ever image of a quasar's event horizon, the boundary beyond which nothing, not even light, can escape. These groundbreaking efforts promise to shed new light on the extreme conditions and processes occurring around supermassive black holes. Despite significant advances in our understanding, many questions about quasars remain unanswered. The exact mechanism by which jets are formed and accelerated to such high speeds is still a mystery. Likewise, the behavior of the accretion disk, particularly its stability and variability, continues to baffle scientists. Moreover, the search for the earliest quasars in the universe has yielded intriguing but incomplete results, leaving astronomers eager to explore the origins of these celestial giants. As we continue to probe the depths of space, we are driven by an insatiable curiosity to understand the fundamental laws of physics and the origins of the universe itself. The blazing accretion disks of quasars stand as some of the most extreme and energetic phenomena in the cosmos, offering a unique window into the workings of supermassive black holes. As we push the boundaries of our observational capabilities and theoretical understanding, we can expect to unlock even more secrets of these captivating objects and unravel the profound impact they have on the evolution of galaxies and the universe as a whole. If you've enjoyed this episode, please make sure to like and subscribe to stay up to date on any future videos on all things space. Until next time, keep looking up.